1, and B, whereas B stayed in that 0 there, which seems incongruent with the phylogeny of the plate. So one possibility that explains this pattern is that there was convergence that essentially means there were two mutations or two transitions from 0 to 1. One of them happening in the branch that leads to what we see today as A, and the other one in the branch that leads to C. Right? An alternative hypothesis, championed mostly by John Avis about 10 years ago, coined the term hemiplasy, involves just one mutation, but rather the incongruency in the trait comes from discordance in the gene tree that underlies the trait that we're interested in. Right? So instead of having two mutations, as I said, we have one mutation in the ancestor of A and C that happen to be more closely related in this particular gene tree. And one of the sources of this incongruency is incomplete lineage sorting. It can also happen through, for example, introgression or HET, whatever you want to call it, but we're going to stick for now to this very simple scenario of the lack of coalescence between B and C in their ancestor that then allows for A and C to find themselves as the most common recent ancestor before B comes in. Or, yeah. All right, so Matt Hahn and I, some of you might recognize Matt from his troll icon there, found ourselves thinking, if you found convergence, or you think you saw convergence in your favorite clade, what is the probability of you being mistaken? Right? That is, what is the risk that hemiplasy is making your traits look convergent? And so we started with a very simple model to address this question. Again, I'm going to do just the minimal Gaussian phylogeny. And the only parameters that I really care about are the mutation rate, or what I'm calling the population-wide mutation rate, when you think about this transition rate, and 3 speciation times, just to kind of 3 time eras. T1 to the speciation time of B and C, T2 that ends up being the most important parameter, and the internal branch, and then T3 for the ancestral branch. And just for simplicity's sake, again, I'm going to start by assuming that population sizes are constant all throughout. Although we can talk about it later if you want to understand how important that is. Okay, so in this very simple phylogeny, we can have 3 possible genealogies. One of them, the one that's leftmost, is congruent to the species tree. And it happens if everything was just behaved nicely. The next 2, the one in yellow and the one to its right, are discordant to the species tree. Right? They're incongruent with that story. And they happen, for example, if B and C didn't coalesce in their ancestor. Right? The probabilities of each one of those genealogies, as I said, are dependent on the length of time that happens in the ancestor of B and C, so T2. If you have more time for that coalescence to happen, then it is less likely that the discordant, the incongruent genealogies happen, and then the possibility of hemiplasy tends to go down. Okay. That's pretty much all we need. I'm going to label those branches lambda 1 through 5 because we're going to be interested in tracking the mutation events that happen in each one of those genealogies, but they're less important for us right now. Just with this setup, we can describe the probabilities of both convergence, or what I'm calling now homoplasy, and hemiplasy. I'm going to walk you through that. So to start with the basic convergence scenario, as I was saying like on my first slide, we essentially have 2 events. We need a mutation in the branch leading to A, and writing it down as a function of the branch in which it happens, and it appears there like an average because we're actually doing it through on the average of all the genealogies, on the 3 genealogies. Then a second event, there's a mutation in the branch leading to C, and then nothing else happening in the tree. Because I'm interested in things that I consider to be really low probabilities, I'm kind of covering my bases and including in the probability the fact that nothing else happened in this history. And also, for just to kind of give homoplasy a nice fair shake, I'm including the possibility of back mutations playing a role. So instead of the 2 mutations that are leading to this pattern that we observe, to be on A and C, then I'm imagining that the first mutation happened in the ancestor of all three species, and then B went back to the original zero ancestral state. But again, it's a product of two mutations and then no mutation in any other branches. All right, for hemiplasia thing, the probability is actually very straightforward again. As I said, the first, what needs to happen is that the discordant genealogy, beta, I'm going to call it here, it's just one of the three genealogies, happens, and that happens with a probability 1/3 of e to the negative T2, again, proportional to the length of time that you have for coalescence. And then one mutation in the ancestor of A and C, and then no mutations in any other branch. And that's really all we need to put together PE for hemiplasia and PO, and we're interested in understanding the ratio of the two. Okay, so these are the numerical results for some reasonable parameter values. I'm showing you on the x-axis T2, again, the length of the internal branch. And then on the y-axis, some reasonable values for population mutation rates. These are contour plots that are showing us where hemiplasia is more likely in the shades of red, and as opposed to homoplasia on the top right of the plot in shades of blue. So the first thing that's striking to me is that there is a pretty steep ridge, so to speak. On the black line, it's a one-to-one line. The events change really quickly. So you can have, with very small parameter changes, big changes to the relative probabilities of the two. Yet there's a very big parameter space, I think, in very reasonable parameter space, where both events are reasonably similar in probability. Just to give you a kind of relative idea of how big T2 is in those very arbitrary 1, 2, 3 coalescent time units, it is proportional to something like 25, 9, or 3% of discordant gene trees in your phylogeny. And I think that those values are pretty common in inferences of like real phylogenies. All right, maybe a second way of seeing this, the value of this ratio, would be to just walk through, or use parameters that we know are real. So we can take the human, chimp, gorilla trio and plug in the values that we have inferred from molecular data and actually use the mutation rates that we have for nucleotides. And so using that mutation rate that you see and those values for the branches, we can infer a ratio of PE to PO, or hemiplasia to homoplasia, of 16. That doesn't really say much, but you can kind of flip it around to say that roughly 94% of bases or nucleotides that you would see with that pattern are actually hemiplastic. In this particular trio, maybe with these particular values, you wouldn't be surprised to know that there's a lot of incomplete linear sorting or hemiplasia with gorilla, human, and chimps. And maybe it's more surprising that I'm also saying the opposite, which is roughly 6% of those bases are convergent, and you're maybe ignoring that particular side of the equation. All right, but we decided to kind of expand this to help our visualization or our conceptualization of the effect of hemiplasia across phylogenies. And we did that with this index that we're calling the hemiplasia risk factor that we can calculate for each particular branch on a phylogeny. So it's really not very different from what I just walked you through in this trio simplified scenario. But we're counting possible events of hemiplasia on both, accounting for both hemiplasia of A and C and B and C, so to speak. So there's two sides to that trio. And then we're putting them as a ratio of all possible congruent observations. So it goes from 0 to 1, and it allows you to color like your favorite tree, like this one from James Peace's work from a couple of years ago. It's the phylogeny of wild tomatoes, and you can see that it lights up regions in the phylogeny that it might be of special interest if you care about some convergent trait. That you don't need data for this. You just have the phylogeny and you want to know how worried you should be about hemiplegia playing a big role in the inference of convergence. But we're trying to take this step forward and actually setting up the pipeline for the analysis of data. This is being led by Mark Hibbins and Matt Gibson. The setup, the thing that we think is going to be more helpful is we're going to allow users, or we want a setup that allows us to simulate an arbitrary phylogeny, allow for incomplete linear sorting and multiple mutations or multiple transitions in your traits, and then it will give you a distribution of the number of mutations and the number of concordant and discordant trees that led to the pattern that you're more interested in. So let me just rephrase that. Let's say that I just have 6 taxa and 2, 6, and 4 marked there in that asterisk, with that asterisk, have the derived state. Right? It is not, these are likely not to be explained with just one event of convergence or just one event of hemiplegia. So to try to understand what perfect mix of events led to the observation that we have, then we can simulate a bunch of scenarios and give an idea of what was the most likely thing. All right, this is work in progress, and I think that I encourage you to contact Mark about this if you're interested in giving it a spin. All right. So it's still pretty early days, but we're hoping that we can get to actual data analysis pretty soon. With that, I would like to thank you for listening, thank my collaborators, and invite you to join us at NC State next year when we're going to be kicking off my lab and the Genetics and Genomics Initiative with a nice training grant for grad students, and hopefully more diversity than a bunch of guys with the letter M in their name. Thank you.